realize at this point I'm the only thing standing between everyone and dinner or beers or something. So, so I'll try to keep it interesting. But thank you to the Hiden organizers, and thank you to all the speakers for doing such a great job. I hope I'll live up to the end of the conference here. So I'd like to tell everyone a little bit about what we've been doing at the University of Colorado with mass spectrometry, obviously, for a DEMS conference, specifically with respect to electrochemical kinetics. And I'd like to say thanks to Abby for doing such a great job talking about situ earlier, because that's what we're going to talk about here today as well. So I'm going to give a little bit of an extended background on what we've been working on with small molecule electrooxidation, so things like CO and methanol, specifically with respect to how do we make these faster using alloy catalysis. Next, I'm going to introduce Sitka, and maybe I'll go through it a little bit more quickly, seeing as how Abby did a great job introducing it. But specifically, we're going to talk about some of the reactor design constraints that we've been considering and how to maximize our response times and whatnot. And then next, I'll give a little bit of an overview of some of the preliminary results we've gotten with our reactor. So CO is an interesting reaction to study because it's a terminal intermediate in a lot of different oxidations. So I'm showing here a CV of methanol. And really, we can think of methanol oxidation first as a decomposition of methanol to CO. And so our CO will block the surface here. And then as we go up in potential, we start to evolve steady-state oxidation to CO2. Finally, as we go to high potential, we start to block the surface with OH. But I want to also point out that this adsorbed CO is not just coming from small alcohols, but also from biomass-derived chemicals, and we've been working a lot about that in the Holowinski group at CU Boulder as well. And so because this is a DEMS conference, I want to put DEMS on the first slide. So we're showing here the ion current towards CO2, mass 44, for both furfural and furan here. And what we can see is that we have kind of two peaks for the furfural, where this first peak is corresponding to the adsorbed CO, which is not present when we have only flow furan, which doesn't decarbonylate. But moving on, the high-performance CO electrooxidation catalysis really is going to require the lower potential adsorption of OH. And so to achieve this, one of the big strategies is using alloys. And so showing here CO stripping voltammetry again, we have this high potential oxidation peak. And this is, again, because we're poisoning our platinum surface with CO. When we introduce an oxophilic metal like ruthenium, we can see the lower potential oxidation of CO when we add some ruthenium. What we're really interested in is the mechanism of this enhancement. So there's the classical bifunctional enhancement where ruthenium acts as a oxophilic donor to platinum sites, as well as an electronic mechanism where ruthenium perturbs platinum to be more optimal for CO oxidation. It's important to note that these effects are not necessarily mutually exclusive and could be both operating at any given point. But what we're really interested in is what are the kinetic signatures of each of these mechanisms, and can we identify real alloys that demonstrate this bifunctional enhancement. And so I'll try to go through this pretty quickly, but essentially we wanted to kind of get a lay of the land, and so we considered a single-site Langmuir-Hinshelwood mechanism where CO and OH adsorb, react on the surface to form COOH, and then decompose to form CO2. We did some DFT, and did computational hydrogen electrodes to get the potential dependence and use scaling relations to develop these activity maps. And really, the goal for this was to get a qualitative survey of the material properties for CO oxidation. And so, I'll try to go through this pretty quickly, but what we were able to show is that platinum lays fairly far away from the activity maximum, shown here by this star. And that's really because of the overbinding of CO, which we kind of expected. And you can see in the corresponding coverage maps that platinum is pretty much always fully covered by CO. And then really if you go a little bit more weak, you get out to the coinage metals, which bind CO very weakly. And so it's difficult for a single material to exhibit the intermediate binding properties required for that high activity oxidation. So the next, we considered a dual site kinetic model, where now we have introduced some second metal to act as a second site type, and we're fixing the first site type to the properties of pure platinum. And so we allow for the full sequence of each step on both of the sites, as well as the cross-site steps. And this is a mean field model, so we've got fast diffusion between sites to kind of neglect some of the alloy distribution effects. And so now really what we want to do is identify the properties of the second site type that might introduce these bifunctional effects. And so just to remind everyone, this is the single site map. And now the two site map, again, just to remind everyone, this first site is fixed to the properties of pure platinum, and now the descriptor space is that of the second metal. And what we can immediately see is that the activity window has been substantially broadened across the descriptor map. And I want to quickly point out the location of platinum ruthenium here in the bottom left corner, laying kind of outside of the bifunctional enhancement map. And maybe this isn't so surprising because ruthenium also binds CO pretty strongly, and so there's going to be a competition between CO and OH on the ruthenium sites themselves. But what we were really excited about is the identification of silver-based alloys here as potential bifunctional catalysts. And for the rest of this talk, or for the rest of this section of the talk, I'm going to focus on palladium. But for the sake of this example, platinum and palladium kind of have the same properties. And so we used a colloidal co-reduction procedure to make a library of silver-palladium alloys. We did TEM, and they're all fairly small and about the same size. We did STEM EDS to show that they're well mixed, as well as XFs to show that there's a Vagaudian Vagaud's law-like correlation of the scattering parameter on the silver or palladium content. And so next we wanted to characterize these using electrochemistry. So we did cyclic voltammetry, or CVs. And I just want to point out a few features. So we have the palladium HUPD, or hydrogen under potential deposition here, which as we go to higher silver contents goes away, which kind of makes sense. And then we also have palladium oxide reduction and the silver oxide reduction. And I think it's interesting to point out that the palladium oxide reduction feature actually shifts in the negative direction as we add more and more silver, indicating that the silver content is starting to electronically perturb the palladium. We also did CO stripping voltammetry, and we can see that when we have pure palladium, we have the nice symmetric CO stripping peak, which we would expect. And then as we add more and more silver, it shifts to earlier onset and broadens out, indicating that the onset potential for the high silver content is going down. So we wanted to move away from this transient measurements and go to steady state measurements to start to have a look at the kinetics. And so we developed this automated gas diffusion electrode, 3 electrode cell setup, which is really nice to be able to get high throughput data. And you might be thinking, you said steady state, why are you still showing CVs? Well, we're scanning at very slow scan rates so that we can approximate this as a pseudo steady state. And what we can immediately see is that under the pseudo steady state conditions, we have a activity that scales pretty well with silver maximizing at the silver 75 palladium 25 catalyst. 25 palladium 75. And then another thing that we see as we go from palladium rich to silver rich is the evolution of this large hysteresis in the CV. And this is due to the oxidation of palladium sites that starts to become more prevalent at the higher silver content. Again, kind of agreeing with the loss of palladium active sites. The electronic perturbation of palladium active sites at higher silver contents. And so then we can also put this on a log scale, and this is called Toffel plot. And so what we want to do from these plots is extract our kinetic parameters to start making inferences about the mechanism. So you can propose a mechanism and get propose a rate determining step, derive a rate law, and start taking derivatives with respect to potential to get a transfer coefficient, alpha, or with respect to reactant activity to get reaction orders. And so we can get these functional forms, which are now related to the coverage of species during the reaction. And we also repeat this whole process with the bifunctional mechanism. We assume that we assume that the coverage of CO on silver sites is pretty low, and so we get this form now. And you can see that they're different, and we think that as you increase the potential, you're going to increase the coverage of this OH species. So alpha should decrease as we increase potential. And then by kind of the opposite logic, the reaction order with respect to CO should increase as we increase potential. So to just give you kind of a little bit of a flavor of the sort of things we're thinking about, if we look at the two forms of our transfer coefficient alpha for the two bifunctional cases, for the two mechanisms, we can then take the derivative of this transfer coefficient with respect to the pressure of CO in each case and get two different forms. And what we really are looking for here is that we would expect the alpha to go up with pressure of CO if the CO and the OH are competing for active sites, in this derivative here. And so showing the apparent transfer coefficient as a function of potential for the 6 different catalysts, we can see right away that what I said before was true, that as we increase the potential, the alpha goes down in each case. But more interestingly, we can see that, especially for the alloy cases, we can see that at low potential, there's really no dependence of the transfer coefficient on pressure of CO. But as we go to higher potential, we see this start to evolve. And what we think this is doing is indicating that at low potential, we really have this bifunctional CO oxidation, and then maybe it switches to the single site case at high potential as we drive OH onto the surface. And so we wanted to dig into this a little bit more using parameter estimation. So I don't really have the time to go through all of the details, but if anyone's interested, I'd be happy to talk to you afterwards. But so we considered the single site Langmuir-Hinshelwood, a bifunctional Langmuir-Hinshelwood, as well as an Ely-Riedel reaction where OH is never formally absorbed to the surface. And as I said, we did maximum likelihood parameter estimation, showing here the solid lines of the fits and the points of the data. So we have reasonable fits. But we can dig into this a little bit more by looking at the coverage maps and the fractions of the rate. And we can see that no one rate is really, or no one mechanism is completely dominating at any given potential, but it's really kind of an interplay of all of them. And so what we wanted to do now is take these parameters that we've estimated and kind of see if there's any trends across the alloys. So I'm showing here the fitted binding energies for the different species as a function of the silver content. And we can see that the CO adsorption is maybe slightly positively correlated with silver concentration, but it's all kind of within error. But we can see that the OH concentration, the OH binding energy, especially the OH star, to palladium sites, has a nice strong correspondence with the silver concentration, indicating that at higher silver contents, we're going to lower the onset potential for these other two pathways. And so our model really kind of described both the bifunctional and electronic effects across the potential series. But so I want to take a step back a little bit and think through a thought experiment here, where we could have two different surfaces. And so the first one I'm considering here is a fully segregated alloy, where all the palladiums are next to palladiums and all the silvers are next to silvers. And then, like a perfect intermetallic where we have silver and palladium fully dispersed. And even though we have the same number of silver and palladium atoms in both of these surfaces, we know that we will have drastically different pair sites here. And what this could really translate to is that for the same alloy composition, these surfaces will have dramatically different bifunctional effects because of the number of pair sites. And so really what we'd love to be able to do is take our steady state reaction data and kind of take a picture of the surface as a function of potential to kind of get an idea of what's going on. And this is where I'm going to transition to talking about Sitka, which Abby talked about so nicely this morning. And so I'll kind of fly through this a little bit, but Sitka is steady state isotopic transient kinetic analysis. It's mostly developed in the thermal catalysis literature. As Abby said this morning, it's not really been done a whole lot for electrochemical systems. And really the key is flowing one isotope over a reactor and then at steady state switching to a different isotopic label and seeing the exchange here, which we can now relate to the residence time and the number of intermediates. And so to just kind of give a simplified picture, at steady state, we're going to flow an unlabeled reactant which will form intermediates, and then goes to products. And then we're going to switch the isotopic label of the reactants, but at some intermediate time, we're going to still have, we'll form some labeled intermediates, but we'll also have remaining behind some unlabeled intermediates, meaning that our product stream is going to be kind of a mixed label. And then as we go to longer times, we'll have full exchange. And so really what this is going to do is it's going to count how many of these reactants were on the surface at the time of the switch and how long they spend there. And so just to kind of nerd out a little bit and dig into the pool models that Abby talked about a little bit. So at steady state, we have some interconnected system of pools that have characteristic exchange rates. And I just want to point out that the pools don't really need to represent a single elementary process, and there's actually no theoretical limit to the number of pools that you can consider, although there are practical limits to how much data you need to fit these models. And so at the time of the switch, we're going to switch the reactant label. And really what this means is that directly at the time of the switch, none of the new labeled reactants have entered the pool system, meaning that this is kind of a snapshot of the number of intermediates at that time. And so, kind of makes sense, but if we could just count these and take a sum of these intermediates, we would get the number of absorbed intermediates on the surface. And so then at some intermediate time, we're going to exchange. And so then this unlabeled rate is going to go down and the labeled rate will go up, meaning that we can also relate this now to the integral of the production rate of the unlabeled product. And then again, as time goes to infinity, we'll fully exchange everything. And so I just want to, so this is getting the number of absorbed intermediates. We also care about the residence time. So we have, number of intermediates over residence time equals rate. And so we can just rearrange this now to get the residence time as well. And you'll see F in some plots, and Abby showed some of those earlier today. This is just a kind of a normalized transient response. So the transient rate over the steady state. I think it's important to note that these parameters, the number of intermediates and the residence time, are completely agnostic to the number or arrangement of these pools. This is just the raw data that comes out of Sitco. But there's a lot to learn from kind of taking different pool models. And again, Abby did a great job of talking about this, so I'm going to try to skip through it a little bit. But the simplest pool that we have is the single pool with irreversible absorption and desorption. So we just have a simple exponential decay transient response, and we can go through this and relate it to coverage and rate constants, and that's kind of what Abby and Ezra were working on this morning. And then as well, we have the parallel pools model, where the reactant will now enter two different pools with two different surface lifetimes and number of intermediates. And again, this is just a linear combination of exponential decays, where x1 here is just the fraction that goes through the first pool. And so what we're really thinking about is how might this Sitco transient look if we have a kind of a bifunctional pool and an electronically modified single site pool. So just to remind everyone what we're looking at here. And so the thought experiment is we're thinking about what this fraction of intermediates, where x1 will be the bifunctional case, as a function of potential. And so obviously if it's fully bifunctional, we expect this to be high and constant, versus if there's no bifunctionality, we'd be low and constant. And then kind of what I discussed a little bit earlier was that we might have this potential dependent where we start off fully bifunctional, and then as we go to higher potential, it changes off. And we might see that this changes as we change the alloy content, depending on whether it's silver rich or palladium rich. And so I've talked a lot about the thoughts behind how to do this. Now we want to actually do it. And so obviously, we need to reach a steady state activity. So we already know we're going to be doing flow reactions. We need to be able to switch between two electrolyte fluids and have two isotope labels in one. And we also want to have an inert tracer to kind of characterize the residence time of the intrinsic residence time of the reactor. And then probably more importantly to this audience, we need to be able to sample the product stream using mass spectrometry so we can distinguish the isotopes. And I think going into this section of the talk, I want to just kind of remind everyone the key tenet for Sitka, which is that the difference in residence time between the tracer and the labeled products needs to only be the time spent on the surface. If there's any other differences in residence time, it's going to kind of contaminate your Sitka data. And so to kind of give some ideas about what we were thinking about when we were designing our Sitka reactor, we started off with some of the more common electrochemical cell configurations. And so, flow of a flat plate is kind of the most basic one. And so in this case, we would have reactant and tracer flowing in, forming a laminar flow profile over the catalyst, and then things flowing out, and we can sample from this exit. And really what this is gonna indicate is that if the reactant and tracer are well mixed, their concentration will be homogeneous throughout this flow profile, but the product is only formed directly at this catalyst layer. And if we have laminar flow and no crossing of the streamlines, that means that the product is only going to follow the velocity profile kind of directly at this boundary here, meaning that the products and the tracer are going to have intrinsically different fluidic residence time, not just the time that they actually spend on the catalyst. So this would result in overestimating the surface residence time. So then another reactor configuration that is pretty common in electrochemistry is using a gas diffusion electrode, or GDE. And so this is going to look pretty similar to the previous case where we have electrolyte flowing in over the top of this GDE, but now we have it backed with gas phase reactants and traces flowing over the back of this, and then sampling somewhere on the backside of this from the gas phase. And really what we're going to see here is that the reactants and the tracers are going to exchange across this GDE, meaning that there is going to be, again, another difference in residence time between the two that is intrinsic to the reactor and not just this time spent on the surface. Additionally, we're going to have a pretty poorly defined gas diffusion pathway here, so GDEs are known to flood to some extent. So fluid will kind of entrain across this boundary, and therefore there's going to be less defined diffusion pathways. Additionally, because some of your gas is going to leave here and some of the products might leave through the electrolyte exit, your sample efficiency is probably not going to be 100%, and depending on how the balance of these, it could actually in fact be very low. And so this is again going to overestimate the surface residence time. And so we heard a lot about this morning, so I don't want to go through it too much, but if we sputter the catalyst directly onto the evaporation membrane, all of the sampled tracers and products in this case will have exactly the same fluidic residence time, because by virtue of the fact that they got sampled by the MS, they must go through the catalyst layer in the same way. But because electrolyte will exit through here depending on the sampling efficiency, and we heard a lot about how the sampling efficiency was quite high, so I think there's some engineering that goes in to maximize this, but it could also be very low depending on how quickly things desorb and the flow rate. But probably a more important thing to point out is that deconvoluting the reversible adsorption might be a problem. And so I talked a lot about the irreversible adsorption and desorption mechanisms, pool model, sorry, but we could actually have reversible adsorption and desorption of our reactants and products, which convolute the Sitka transient, but aren't intrinsic to the surface residence time. And so typically how people do this is they measure the residence time as a function of flow rate and kind of extrapolate back to infinite flow rate or zero residence time. But because this reactor configuration isn't going to allow for kind of this exact relationship, deconvoluting this reversible adsorption might be tricky in this configuration. And so now to tell you about what we've been doing, and our approach is really inspired from thermal catalysis and specifically using a packed bed, which is kind of the traditional Sitka method. And so really what we're going to do is we're going to take our electrolyte and our reactants, and we're just going to flow them through a catalyst plug here. And what this will do is it'll allow for a homogeneous, if we have a well-mixed system, allow for a homogeneous plug of reactants, products, and traces to come out of this that we can sample with our mass spec. And we should have reasonably high sampling efficiency because the plug should all kind of cross the mass spec. And importantly, we should be able to deconvolute the reversible adsorption-desorption by varying the space velocity in this configuration. You don't hear a whole lot about packed bed EChem reactors, and so we spent a lot of time trying to figure out, and we're still spending a lot of time trying to figure out how to actually do this. So to kind of tell you about what we've done, we took our block of plastic, we drilled some holes in it so we could get electrolyte flow, and then we put our DEMS capillary and our reference electrode in the flow path so that we can sample here, and you can kind of see the very dirty reactor, but there's a little flow channel right here that the electrolyte will flow through. And then what we'd really like to be able to do is just put a tube with a packed bed kind of right here. But then the question remains of how do we make electrochemical contact for that? And so what we've kind of come up with is if we put a gold TEM grid in this flow recess right here, the packed bed of this reactor will push up against that TEM grid and make electrical contact with it. And then we seal everything by putting a graphite ferrule that touches the TEM grid with a steel screw, and we clip our potentiostat cables onto this steel screw to make contact. We mirror this on the flip side to make a counter electrode as well, and this is kind of a picture of our setup here. And some of the challenges is that, reliably getting this packed bed together is kind of a challenge, and so sometimes it takes multiple setups to get the reactor together. The cell has fairly high resistance at this time that we're trying to kind of solve that issue. And the electrochemical and mass spec signal are pretty sensitive to peristaltic waves if you don't have the pump set up exactly right. And so I want to manage expectations. This is very preliminary results. We're still actively working on some of these things to try and clean them up a little bit, but I wanted to share some of the stuff we've gotten so far. And so just showing a plain platinum CV on our 80% commercial catalyst. We can see the big tilt here which is our resistance, but it looks more or less like platinum. And then we can add formic acid and do formic acid oxidation, and this is where you see some of these peristaltic waves coming in. And with formic acid, we can do a CO2 calibration because formic acid oxidation is stoichiometric to CO2, so we can vary the current and get a calibration for this. And so then once we have a calibrated mass spec signal for CO2, now we want to see if we can do methanol Sitka. And so now switching from formic acid to methanol, we can measure a CV, and really what we want to do is at different potentials along here, we want to do our Sitka measurements. And so we have here the exchange of the labeled CO2 and nitrogen, and we can see the area here is the difference in the residence time, and so we can integrate that and get the surface residence time, and then we can vary the potential and get different responses. And so from these residence times, we want to back out the number of adsorbed intermediates and compare it to other catalysts. And so just comparing two different commercial catalysts that have different amounts of platinum, and we think that the difference in particle size is different here, so we might expect some differences in residence time, although we see kind of roughly similar residence times for each. And then, when we convert this from residence times to a number of intermediates, we see that the 80% platinum has slightly more adsorbed intermediates, but again, I want to assert that this is preliminary data. We don't really have any concept of how large our error bars are for this, but we might be able to say something in the future about the nature of the active sites being edges or terraces based on these ratios. And I want to conclude finally about something that I tried to sneak by you earlier in the talk, which is that all of our bifunctional catalysis work is done in alkaline media, so in basic electrolyte, and CO2 quantification, which we've actually heard from a few other talks today, being kind of a challenge in that case. And so some of the work we did with the Bedford group at the University of New South Wales on urea oxidation. So urea is kind of a bad thing for wastewater, so we want to try to convert that to something else. And we want to convert it to environmentally benign products, so not nitrates and nitrous oxides. And so we did this on these layered double hydroxide catalysts, copper cobalt and nickel cobalt, and we can see that the copper cobalt has kind of a very favorable urea oxidation capacity, and we actually found that the copper cobalt catalysts also predominantly forms nitrogen versus the nitrous oxides that are formed by the nickel cobalt, so that was really nice. But we were expecting to have to deconvolute the 44 signal here from N2O and CO2, but because this is all done at pH 14, the CO2 equilibrium with bicarbonate is pretty rapid. And so when we do just formate oxidation on these catalysts, we see absolutely no formation of CO2. And so we might be able to get away with pH 13, but we're not actually sure. And would love to see if anyone has any ideas on what directions we might be able to go to get to that point. And so, as everyone knows, it takes a village to raise a PhD student, so I'd love to acknowledge all the different funding agencies that I've had, as well as my PhD advisors, Adam Holowinski and Charles Musgrave, as well as the Bedford group, and especially UA, who did a great job on the urea oxidation paper. And of course, to you for your attention. I'd be happy to take any questions.
Questions, but so many that I haven't quite formulated most of them yet.
We can talk later.
Yeah, we probably should. But I have a couple questions for you. One related to the Sitka. You know, it's nice to see other folks working in this area. I think it's a very important emerging area in electrocatalysis. Couple questions about your setup. How fast can you flow through your packed bed, and do you have any concerns with the chromatographic effect? So things like your tracer are not going to reabsorb to the catalyst bed as it passes through, but your products may have some interaction with the catalyst bed, you know, after they've desorbed from the site in which they were formed. So how do you correct for those effects?
Yeah, great question. So I don't have it on these slides. I might have it in a backup somewhere. I can show you afterwards. But we've actually characterized the bed length and also the loading of Vulcan that we put onto. So we make a catalyst ink and deposit it on there. And we've characterized both the amount of Vulcan that we put on and the length or the mass of the bed that we use. And we find that if you use fairly low bed lengths, which all the data that I showed was using that, we don't actually show any CO2 reabsorption. But yeah, absolutely. If you go to higher and higher bed lengths, you will kind of get that chromatographic effect.
So you keep your bed length pretty short. Do you have an idea of what kind of electrochemically active surface area you have in the bed under those conditions?
Yeah, so I mean, I don't know if you looked too closely at my CVs. They're not the best, and that's something we're still trying to work on. But I don't know off the top of my head what the ECSA is. So to give you kind of a context of how much catalyst is in there, we take probably like a fingernail's length of plain carbon cloth, a single strand of that carbon cloth, we like pull it off, and we deposit, a few microliters of our catalyst ink onto that, and then we kind of crush it and stuff it in there, kind of like a musket. And so there is a pretty tiny amount of platinum actually in the packed bed.
Okay. Thank you.
Any questions online?
I just have a sort of a question on the pump. Have you considered replacing it with some other style of pump?
Yeah, of course. I knew that question was going to come. Yes, we have tried syringe pumps, and obviously it smooths everything out. But there's some other kind of problems with using syringe pumps in that you have to use it in a pool configuration to make sure the electrolyte stays degassed, and then there's a whole bunch of other issues with doing that. And so you can, and I think actually Ezra showed or Ezra and Abby showed in their lab tour, there's some tricks you can use with the peristaltic pump. And so I've actually implemented some of those now, and we're cleaning up the peristaltic pump noise as well. But you know, if it's not one thing, it's another. And so I couldn't quite get everything ready and to show like nice data for this talk, unfortunately. But
Oh, it's really, really cool, cool setup you guys have.
oh, thanks.
Thank you. Thanks for the talk. I'm excited that you're doing Sitka too. That's very awesome. But I do have a question. So this is your Sitka reactor schematic, sort of, correct? This blue schematic right here?
No, this is we're using the packed bed configuration here. This is the straw man that I set up.
Okay, but so you do have an inert. You are monitoring an inert while you do electrochemical Sitka, correct?
Yeah, so we have in one of our electrolyte bottles we'll have nitrogen, and the other one we have argon, and so we can characterize the exchange of the traces as well.
Okay, so but how does when you're monitoring this in the mass spectrometer, how does your data acquisition compare for these inerts versus your products that you're actually producing? Because you're monitoring them simultaneously, right? You're monitoring your products and your inerts at the same time. Is that correct?
Yep. Yeah.
So what is that? I'm imagining that your data acquisition for these inerts is significantly slower than data acquisition for something that's much more abundant, or I guess not necessarily abundant, but for this CO2, let's just say.
Yeah, it's a good question. So argon actually is pretty soluble in aqueous systems. So our electrolyte does have a fair amount of argon in it, and we're not producing loads of CO2. Our current densities are pretty small. So the order of magnitude for the signals is fairly on par. So we don't run into issues where we have way too much of one signal and not enough of the other. That's one thing that we don't have to deal with.
Maybe we'll finish one more question. I'm just curious about going back to your catalyst. You talked about that there was some evidence of electronic modifications based on the shifting of the palladium reduction wave, and I'm just curious, have you done any sort of XPS or electronic structure characterization to look for any evidence of those kind of electronic modifications?
Yeah, thanks. We have a forthcoming publication on in situ X-ray absorption spectroscopy, where we did Zane's Zane study of these different alloys with and without methanol, and yeah, stay tuned.
Great.
Sorry, one more question. On slide 10, just because I do a lot of CO stripping, I'm just curious. It's kind of an irrelevant question, but on slide 10, you show that this silver and palladium alloy, and you show CO strips over them, as a function of, I guess, concentration of either metal. And you see that, I guess, I'm not sure which metal you had more concentration of, but you see that when you have more concentration of one than the other, I guess of silver, your CO strip peak becomes much broader. And what is the fundamental explanation of something like that? Like when you have a broad CO strip and peak, that broadening, what does that really represent? If you
Yeah, it's a good question. So it's much easier to think about when things shift negative in terms of the alloys because we're oxidizing CO at lower potentials. I can't readily speak to why the peak might shift, positive of that, indicating that we're oxidizing some amount of CO at later potentials. I can't readily say why that might happen, but when things shift negative, it's because we're just oxidizing them at a lower potential.
Sort of seems to suggest that the surface has a wide distribution of active sites, and when you do Sitka on such a distributed system, you're going to get all kinds of, each site is going to have vastly different activity. So how do you envision using the Sitka data to kind of tease out the critical information? Because I guess you're really after the kind of average residence time, which is kind of an exponential average of all the different sites that are there. So how do you work up the data at the end of the day?
Yeah, hopefully that's someone else's problem. I'm joking, I jest. No, so yeah, it's a great question. And like I said, there's no theoretical limit to how many pools you can fit. I mean, you can stick as many in there as you'd like. Then it just becomes a question of data quality and statistics. If you add enough parameters, anything will fit, but then you have very little confidence in that. And so there is a question of how good can our data get, and we'd love to, talk about ways to continue improving the quality of our data. I imagine that if we can get to a point where we can fit two different pools, one where we have a bifunctional mechanism depending on, as you said, like kind of an average of that, and one pool being the single site or Ehlers-Danlos type fit, I think that would probably be a pretty significant accomplishment. Actually teasing out all the different nuances of, some palladiums might be at the edge and all that. I really doubt we'll get to that point. The data quality just probably isn't going to be there.
Todd, thank you so much again. Really appreciate it. Thank you. Thanks. Can I just say a big thank you to all the presenters today. This has been our first attempt at such a webinar here in the US, and it's been phenomenal. All the presenters, thank you so much, both here and, of course, Moon and Professor Asadi back home. We truly appreciate all your work in preparing for today's meeting and taking the time to join with us. We really do appreciate it. Thank you so much. Thank you too to Penn State for all your hospitality in hosting this event. The guys here have been phenomenal, so helpful. It's really been a pleasure working with you all. I do hope that we can all meet again and repeat this. It's been fantastic. With regard to today's presentations and videos, these will be available shortly from our website. That's www.hidenanalytical.com. To our viewers, both live and those watching offline, you're welcome to reach out with any questions via our website or our inquiry email address. That's info@hideninc.com. So if you have any questions at all, please reach out to us on info@hideninc.com. We do wish you here and those viewing online much success in your future work. And we look forward to meeting with you all again very shortly. Again, thank you so much for taking time to travel with us. We wish you safe travels home. Thank you so much.